as I talked about Monday, that we have been focusing on this course, generative AI, which is a very buzzword these days. Everybody's talking about AI, and in particular, this is computer vision, generative computer vision. So we started with the whole revolution. Started with the large language model, the ChatGPT, LLM, but we have focused in this course because advanced computer vision. We have focused on the visual language model or large multimodal model, right? We have spent quite much time on that. And your assignment 3 will actually get you really in depth of these top of the line visual language models, 3 of those. So now the other way to do generative AI is to actually generate images. In the first one, we're generating language, text. So then diffusion model is the way to get very realistic looking images, the videos and audio and so on. This is also the hottest topic you hear every day in the media and Twitter and so on. So the idea is that you want to be familiar, at least know the basics, how the diffusion model works, how you can generate images and video. Of course, there's a lot of work happening in this area, and there's a lot of math, a lot of background, and actually we have different courses which are touching upon this kind of material. So we have a course from EC department, Dr. Wang, he's covering a lot of math related to diffusion model, about half of the course. So then there was another course Dr. Bedi taught last semester, which covered also diffusion model. So there are a lot of intersection in different courses because that's the whole nature of the research right now, because at the end that there is one unifying theme which you can apply to different areas of the AI and computer science, which is very interesting. So so what this kind of introduction will give you, that at least you would be able to talk to your friend, talk to your grandma, what are you learning? So you can tell him here that this one is, there is this kind of Twitter, I follow this guy. So he will show you every day, he has about 10, 15 kind of videos, and amazing videos he will show. You can generate using diffusion model, right? So this is amazing. You can, these are, realistic looking. There's no way you can distinguish, and it's happening. And you are learning that, in this class, basics. So that's what you need to actually appreciate and really benefit from to educate yourself. And there's another guy also. So these are links, you can follow this guy. Okay, so we started the basic method, which is very simple to understand and implement, is called denoising diffusion probabilistic model, DDPM. Okay. So the high-level idea of these diffusion and probabilistic models is that we are taking an image, as I said earlier, we are adding a noise, and basically we are destroying the data, okay? And the process we do, so this is called forward process. So we start with some data set, like ImageNet or CFAR or Celeb A and so on. So there's a data set. And from there, we take and that data set has some distribution, which is shown here, okay? And that's a high-dimensional space, but here I'm showing just one-dimensional space. So from that distribution, we pick one sample, and we go through the forward process. We keep adding noise and noise. So of course, this sample from this distribution of this, say, Celeb A, but now we want to make it that it becomes the sample from the normal distribution, Gaussian distribution, zero mean, and identity covariance matrix. So that's a forward process. And then the reverse process is that you can sample any sample from this Gaussian distribution, and you denoise, and then come up with a sample which looks like an image, which is amazing. It's a magic. You start with a complete noise, and you get the image which looks real. And people are having a hard time distinguishing real and synthetic. So, so of course, this is this is the unconditional generation. So we can we generate an image from that particular data set. Suppose celeb A has lots of celebrities, but when we sample from this random sample from this distribution, it will be some image, but we don't have any control which person it is and so on. And of course, it will be a new. So it's called unconditional generation. There's no condition, okay? And we're going to talk about later how to generate the conditionally giving a prompt or a particular class. So then the process, again, you take an image, and this is a Q of X, an original distribution. We take a sample from there, and it approaches to NT X of T, which is the normal distribution with zero mean and identity covariance matrix. And then we go through the process of the denoising, reverse process. We sample this and becomes the actual image, which looks like an image as compared to start from noise. So we talk about now the main thing is that we are learning this whole ideas in AI is you learn something from the data. And so you have to train the network to be able to denoise. You add a noise, you put in a network, it will denoise, okay? And whenever you want to denoise, when you want to train a network, then you have to know what's a loss function. You have learned this loss function, say cross entropy, with a very simple loss function in the classification. So here the loss function is this one, as we went through on Monday, that we have a z theta, which is a network. Input to that is xt, and time. Every time step, we have to input how much time, which time we have and how much noise we have added, and it will predict the noise. And we went
Excuse
through,
me, Professor.
and this is called, yes, sir.
We can't see your slides here on the Zoom.
So that's what, okay, so let's try again.
I can't see the slides, by the way.
I can see too.
Everybody can see it, okay? So maybe you have some difficulty, sure. Can you
There
check
are like
again?
2 tabs on top
Thank
of
you.
it.
Yep, I see it now. Thank you, Professor.
Okay, good. So this objective function is called L simple because we're simplified. So, and we talk about the training algorithm that and this you can write a code, very easily, and this actually you should. So you take for a particular data set, say C4, celeb A, and so on, and sample image x0 from that, and then you come up with a uniform distribution of the time. You sample that time step, and then you sample the noise from the Gaussian distribution with zero mean in identity matrix, and then you add to x0 the noise, which is zt, and these beta t and so on are how much noise you are adding, what is your schedule, and so on. Beta is normally less than 0. And this is where every time step you will add the noise, and you will get xt. Now, once you have xt, then this is the objective function. You put an xt, you t. Now you want to find the gradient and then update the theta parameter based on the whatever gradient you get. Very, very simple, very intuitive, and you should actually do that. And so these are the different steps we went through last time also. Okay, so now the way to do it, that the network we are going to use is called UNet. That's where it started. UNet is like autoencoder. You put the input is an image, output is an image, and input here will be a noisy image, output will be a denoised image. And this will go like this, and then time is also input, and then it will estimate Now, in this thing, you can estimate the noise, or you can estimate the mean of the noise distribution, and there are different versions of that. Once you know that, then you can sample from that distribution, you generate an image, right? So it's very intuitive, very simple, and you want to be able to code this and try it out and so on. So once you do that, now you have this distribution. Now you want to sample from the distribution. So one is called the training, other is called sampling. Then from that distribution you take the xt from normal distribution. You go through this process, t is equal t to 1, keep denoising, and then you can generate xt minus 1 from xt. And you keep doing that, then at end x0 will become simple. So that's a sampling algorithm. Okay, so now we are going to discuss another method, another formulation of the diffusion model, which is called noise condition score network, or score network, score matching, and there are lots of different names for that. So this is a little different, and here instead of looking at the probability, we are going to look at the log of the probability distribution and gradient of that. So this is a gradient of log probability, and it essentially tells the process that you have a probability density function and you want to find out, the direction where it's changing the most. Okay, so suppose here is the mixture of two Gaussian. So the probability density function, we have only two Gaussian, one here, one other. So in the 2 dimension, it looks like that. Okay, so the score function or score matching is showing that the gradient, the direction where you should move to maximize this density. Okay, so so this giving you a direction. We need to change the input x so that density becomes greater. Now, once you can estimate the score function, then you can actually generate a sample, draw a sample from the distribution, which is given here, and this is called Langevin dynamics. So main thing is, if you know this gradient of probability, delta x dog p of x, then, and if you know where you have omega as a noise, then you can take from xi minus 1 to xi. So therefore, very simple naive score-based model is essentially that one again, that we are going to find a gradient, and we want to use the Langevin dynamics to draw a sample from the distribution. So this is our estimate, will be estimated by a score network. We are going to train that as we train in the DDPM. And this is the noise, as we had noise there, Z. And then this is step size, how much we want to move in that direction. Okay? So now, in this one, again, we need to have what is the objective function to train this S theta, which is our network, and this will be essentially, since we know the what's the definition of the score function, gradient of log p of x, and we want to make the difference L2 distance between them to be as small as possible. And after the training, then it's become approximate that the actually score function. So this, once we have that, then we can sample using this Langevin process from these two Gaussian. These samples will come from those because these are centered in these two places. So now the process will be, you again have a sample, you have a data set, whichever data set you pick, and then you compute the S theta, learn the S theta, and then you can use a Langevin dynamics to generate new images. So now, but this is a pretty simple, what they call naive score-based model, and it has some problem because the real data resides in low dimensional manifolds, and the score function is undefined in those areas. So therefore, we have a difficulty, and we will end up incorrectly estimating score within that low density regions, and we want to fix that. So, so here's an example. So let's say we have this density. We have only these two places where we have some samples, but we don't have anything in between. Why this is shaking? I don't know. Let's see. It's again a mouse problem, I guess. So we can estimate the score function at the the area where it's accurate, where the data source is accurate, will be happen, but the other area in between will be inaccurate. We won't have real score function, and the score function is the arrows. So what we are going to do to fill in those gaps, as you see, there's nothing between these two where we have density, and this, this is the third time we have told them to fix the cursor. It doesn't work. The mouse just keeps shaking. Okay, so we are going to diffuse that. So we are going to actually add noise. We will perturb that. Now it's become better than what we had before, as you see here, right? So then we will have better perturbed score, and we can estimate that score better. Okay, so so this is called noise condition score network, right? Other was naive, where there was no condition of noise, and perturb the data, random Gaussian noise at different scales. So we will have the sigma 1, 2, 3, and you see that's become very similar to DDPM. That's what we were doing there, right? And then we will learn these score estimates from noisy distribution while single network. And so this will become the score, and then if you take an image, we'll perturb like this, we keep it in noise, it will look like that. And now as you see that we have P sigma I. There we had just a P of x, log of P of x, gradient of this. Now since we are adding the noise condition, so we are going to introduce the sigma I. So therefore to the network which we are going to learn, the input is not only x but I also, that how much, which level noise we are adding. Okay, so it will look like this now. It's much better because we have diffused these, and these are different level of the noise, sigma 1, sigma 2, sigma 3, and so on. Okay, and if you do that, then it's a CFAR 10 and CELAB A, you can generate these kind of images. Okay, so now if you look at this, so we have a sequence of Gaussian noises, and we start with the first sample from the our data distribution, and then we get the sample of this P sigma T from again the noise will be Gaussian, zero mean identity matrix, and then we are going to have this forward process, and this will be a Gaussian. And now what we are going to estimate will be actually the gradient, log gradient of that, right? So this is exponential. If you take a log of exponential, then it will disappear, and you take a gradient of this. So gradient of this xt minus x will be what? If you differentiate xt minus x whole square, what will be a derivative? Yeah, so this will be a derivative, right? This is a gradient. So xt minus x upon sigma t square. So there's a very simple log, gradient of log Gaussian will be xt minus x upon sigma t square, which is variance or standard deviation of the Gaussian. So it makes very, very nice, simple expression, because we have exponential. Take a log of that, exponential disappear, then we square, then 2x, and derivative of x, which is 1, divided by 2 sigma, and all this thing. So that's it. So therefore, the objective function for the score matching is that we are going to learn S theta. Network input is xt and sigma t, how much noise we add, and the ground truth is xt minus x upon sigma t squared. So, and this is the algorithm for training this network, okay? So if you go a little bit detailed, so we are given a data set. You can pick your data set, and we have noise levels from sigma 1 to sigma L, and learning rate and all this. So we will initialize S theta randomly, and then for each of these, we will take a mini batch from the data, and we will have these sigma 1 to sigma L, and then we will sample the noise EI. We'll add the noise EI to XI, it become XI head, and we will input that to the score matching function S theta, and the ground truth we know is the XI delta minus XI divided by sigma square, and then that's it. So in order to learn these parameters, we'll just use this objective function and update the parameters and so on. So this is the theta will be updated by finding the gradient of the L DSM, which is given here, and I show you, the expression for that. So this was the training. Now you can, once it's trained, you can sample it. You can generate a noise, generate a sample, and it's very similar to now. He is annealed because we have different level of the sigma. We are slowly changing the sigma value, and we have number of iterations. We have sigma 0, 1 to 0 t, sigma t, and we update the magnitude, and we sample the x0 t from normal distribution and go through these two loops. One is for the time t, other is for the one, I 1 to n, and we sample the zt, and that Langevin equation I told you, the only thing is we have introduced here sigma t, and which noise we are adding, and we getting xt I minus 1, we will find out I. So at the end, we will get the x0. We go through for each of these iteration for all the noise levels. At the end, will come up the x0. So it's very similar to what we discussed before for DDPM. So, and sampling will be the same thing, that we sample, we start with the normal distribution, and we go through, this is, I think, going in detail. Yeah, I actually went through this. Okay, so now, as you can see, they are so similar, right? The DDPM and this score matching are very similar. We're taking an image, we're adding noise, and in one we were just, estimating a distribution P from Q distribution, we are estimating a P theta. Here we are just estimating the log of the probability, the gradient of log of probability. So, and in both cases we are adding noise and all this thing. So actually you can show that these objective functions which we are using to train these networks, they are actually very similar. So this is objective function. If you remember that DDPM that we are learning, we are training Z theta, input was xt and t, and we know how much noise we are adding zt, and this is the score, the objective function I just explained for the score matching. So again, here S theta has the xt and sigma t, and That's what the estimate, and this is the ground truth xt minus x0 upon sigma t square, because it's a Gaussian. We find the derivative of that. Okay? So now if you look at a little bit more detail, ZT, if you remember the way we did it in the DDPM, that we are taking x0 and we are adding the noise, which were depending on the ZT, which was sampled from normal distribution, and sigma t. And so if you take this equation where xt is equal to x0 plus sigma t and zt, we can express zt like this. Zt is equal to xt minus x0. And this is so annoying, you know, this thing just keep blinking. I don't understand what's the problem. Shall we try to get out and then do it again? So it works here, right? But it's still blinking here. Okay, try again. Sorry, where we were. Okay, so, okay, now it's good. So what I'm saying here, take this equation and express this zt on one side and bring everything back on this side. So xt minus x0 divided by sigma t, so zt, and which is zt here, which we use, which was a ground truth when we are training the DDPM. Okay. Now, if you look at this one, what we are doing, the score matching, is xt minus x0 sigma t square. So this is xt minus x0 sigma t, and this is xt minus x0 sigma t square. Very, very similar. It's exactly the same, only it's different as sigma. So that's why these two different processes at the end, when we are learning, we are doing basically the same thing, which is pretty interesting. And it's very interesting for the theoreticians, you know, for the math. Okay, so now again the sampling also very similar. So again, try to understand. So one is that we have the distribution and we are learning that. Once we have distribution, we need to sample and generate a new sample, generated image. That's what we are looking. So we talk about, to train the network, what's the objective function? Because always you have to have objective function. You learn the parameters of network, like unit parameters, by minimizing this objective function. And once we have done that, then we want to be able to sample from that distribution. So suppose in this case, we know z theta, we have learned it. Okay. So now we will put the xt and t, and from there we will generate xt minus 1, and we keep going until we have the x0. So also a iterative process. And this one is for the score matching, very similar to this one. And here we also have xti minus 1. From that we get xti. And this is what we have learned. We can plug in this, we get value, and these are other kind of easy things. And so the sampling and training objective is similar. Sampling is very simple, similar process. And so in the DDPM, in this score matching, this is our objective function, and then we can rewrite this. We can bring in minus here now. This will become xt minus x, will become xt minus x minus that, because there was a plus here. And then this is from our DDPM, which is zt minus z theta and so on. And then we can see that zt is actually xt minus x0 and sigma t. Okay, so that is about two methods, DDPM and the score matching to do the diffusion model and how to generate new images. So far, we have been able to generate images, any images from that data set. So if we are going to use the, for example, ImageNet, which has 1,000 classes, so when we take a sample from Gaussian distribution, we go through the process, it generates some image, but it can be any of those 1,000 classes. Right? So we don't have any restriction. We haven't introduced any condition that these images are, say, the airplane class, and these images are for the dog class, and so on. So that is called unconditional image generation. So we are going to talk about how we can introduce a condition, because condition is more interesting, that we want to generate images for particular type, particular class, and particular prompt, and so on. So condition generation can be class condition, it can be text condition, prompt, or it can be image condition. We input an image and generate a new image, say, do a segmentation or in painting, and so on. So that's become more interesting, actually. Okay, so now we talk about that this score matching, essentially, that we have the gradient of log probability, and once we estimate that, we can, it is sampled from distribution P of X. Now, when we introduce the condition, so this probability P xt or Px will become condition. So probability of X given Y. This probability will be for a particular class, right? So Y is a class, Y is a condition. So therefore, then we will have the gradient of this probability Pt xt given Y. Okay? So that will be the change. And now, so one simple way will be that we'll do the conditional training. So we'll train a model with additional input Y to estimate this log probability, and which can maybe look like that. So we have a unit, we take an image, typically we just put a T, but now we can put a Y also. And then we will get the gradient of like that. So that's one, very simple. The second one we can, now the problem with this is that we want now estimate the log of the gradient of log of this conditional property, and that will be a change. Now the second thing is that we can actually train a classifier, which is called classifier guidance. Okay, so here is a very interesting idea. So the Bayes rule. So because we have this conditional property of xt given Y, as you know from the Bayes rule, we can express this conditional property of Y given xt. So this is the marginal property, this property of xt, property of Y, and this is probability of Y given xt, and this is equal to probability of xt given Y. So we can go other way. Here we are given xt, we want to find Y. Here given Y, we are going to xt, and we are going to use this to help us to come up with a classifier free guidance and so on. So this is very important. You will encounter this Bayes rule a lot, and it's very powerful thing. It's very actually simple, relating two conditional probabilities. Okay, so now if you take because we have been doing the logarithm and gradient, right? So that's what we are going to do. So we'll take the log of these. So log of pt, probability of xt given Y, log of this pt y given xt, and this is a product. So when you take a log, it will become plus, and this is a division, so it will become minus. So this is standard thing you do. So now we'll take a gradient of that. right? We want to find the derivative of that. So gradient of this will be that, and this will put a gradient here, and gradient of ptxt, and gradient of log pty. So which is shown here. Now, what will happen to this one? It'll be 0 because we are not. This doesn't depend on x. Okay, it's just a marginal probability of y. These two terms depend on x. This also depends on x because it's even though the probability is y, but given x, it depends on x. So therefore, it becomes like this. So now we have this, and so if you interpret this, this is the unconditional, diffusion. That's what we have been talking about. Just probability of p, log probability of xt, and gradient, and now this is a conditional probability, right? Depending on the. So we can train a classifier, which will, given x, it will classify which class it is, and we can do that. This is the second solution. So here we are doing classifier guidance, okay? So, and you guys have learned how to train a classifier, you can do that. Now, the problem with the classifier guidance is, and you can, decide that the images you want to generate, how much you want to weight to particular class, and then how much you want to just generate images from whole data set, diversity versus, general, particular specific classes. So let's say you want to generate images of hamster. Now, if you put the s is equal to 1, which means it will generate images of unconditionally images of that particular data set and conditional images equally. So these will not be really, hamster images if you want to generate that. So then, but if you increase, then you will get a better, mostly all these samples will be hamster images. So you can weight that. So that's a weight of this thing. So now the problem, this fine problem is that, you want to use the classifier, which is here, this classifier. This is a classifier, right? So you want to, given x, and you want to classify it, and you want to do that log of that and all this thing. So now this, as you remember, xt is a noisy image. You are keep adding noise. So training that classifier is a problem, and it will not be robust to noise, and which would be a problem. So that's why we don't want to do that. So very interesting thing is called classifier-free guidance, that you can do the conditional generation, but you don't have to use classifier, which is very, very nice, and listen carefully. It's very interesting. So again, we said that we want to have this conditional generation. We have two terms. One is an unconditional one, and other is a conditional one, and this was using classifier, and this S is the factor to balance how much you want particular class and how much you want the general from the whole data set. Now again, we are going to use a Bayes rule. So Bayes rule, you should be very comfortable, and so it is saying that now we want to say probability of y given xt can be expressed probability of xt given y, and so on. So let's take the logarithm of that, becomes like this, and then we take the gradient, and we did this before, because here, the does not depend on x, so we will make it 0, and so now we are going to use this fact from here, because this is what we want to do, the classifier-free guidance, a conditional generation. So we bring in this thing here. So this is a gradient of xt given y, which we have here expressed. Now what we are going to do from this above, we are going to get the expression for this term. We will take this one and plug in here. Okay, So, and this makes sense. We have done this. So we will take this one. Instead of this, we'll put this expression. Okay. So now when we do that, so this is replaced by this, the gradient of log pt xt y, and minus gradient of xt log pt xt, and this will repeat like that. Okay. So now as you see that we have this gradient of log pt xt, gradient of log pt xt, these two terms are the same. Of course, this is multiplied by s, and this is just 1, so we can group them. Okay. So then we will have the s gradient log pt xt y, which is this term, and this term will become minus s, and this is just that. So it will become 1 minus s gradient of log pt xt. So we now have that this is the unconditional generation, and this is the conditional generation, and this in a way that we are given the y, which class we want to generate the image. So it's different than other class we were looking at, which is shown here, that we here given an image, we want to find out what class it is. So this is the classifier. Now here is a classifier free, because this is very similar to this one, but only condition y. So then what will happen, that we can train one network where we will put the condition y like this, and the way we will train, so sometime we will have null, we will not put the condition, sometime we will put the condition y, and that will satisfy our equation, because we have same network which is being trained using this thing. So again, I think mouse is having a problem. Okay, so let me look at this one. So so we have one network which is depending xt input, t as input, and y as input, which class we want to generate. And so we will, in one case, we'll put the y. In other case, we'll put null. We will not put any class. And so that will be one network we'll train, and we will not use any classifier, but it will achieve the conditional class generation. So instead of training a separate classifier or doing these other things, this is the pretty nice way to do the classifier-free guidance of generating the diffusion, images using this score matching and so on. So that's, now in this one you can actually do not only the class, but you can also put the text. We have the same idea. You can put the text encoder and bring it there, or you can put another image as a condition. We'll look at one day the stable diffusion, which is big impact, which works pretty well. You can do all kinds of condition there, and it will work that same idea what we are talking about. Okay, so that I think completes these two important model of diffusion model, the DDPM and the score matching or score function. They're different phrases people use, and the main thing is that it's looking at the probability of the data, and probability of data is important, as you know, that when you even train a classifier, you are taking the data set, which is some probability distribution, and you want to, and you have a distribution of the ground truth of that particular, if you have 1,000 classes, you have 1,000 dimensional probability distribution, you put an image and you want to come up with a probability distribution that what's the probability that this image belongs to this particular class. So that is what it will predict the network, and your ground truth probability distribution, you minimize the difference between two distributions using cross entropy. So the probability distribution data, whenever your data, you have to have probability distribution. What is the distribution, right? So, so here, what we are trying to do is we have some probability distribution of the data, and we want to learn the network so that we take a sample, we put a noise, and so on, that maps to the Gaussian distribution, random noise. It's complete white noise. Then we sample from the noise, and we go back and will become a new generated sample. So in order to do that, so main thing here is that how you learn this network, which will take a noisy image, it will denoise, and how many steps of the noising you want to do, and how quickly you want to do, and so on. And so that was unconditional image generation, and you can apply the same thing for video generation. You can apply the same thing for the audio generation. Same idea, because here we haven't assumed anything. It can be any data, right? It's a probability of X, so that X can be 3D. You can do the LiDAR. You can do audio, music, images, MRI, and so on. So you can do also on the proteins. The Nobel Prize, which was awarded last year in chemistry, they synthesized, they generated new proteins. So proteins is again a data. You get a lot of proteins, and each protein is a sample in the data distribution. And of course, protein, you represented a structure that you have molecules, you have X, Y, Z coordinate of each of the molecule, and you represent that. It becomes some vector, right? Some vector or graph. So you take whatever proteins you know already, like ImageNet data set, we know all the images. So you take this protein data set, you train this diffusion model to learn to generate new proteins. And new proteins then can be used for vaccines and so on. So very, very nice, innovative way, because this professor from University of Washington who got a Nobel Prize, he came to CVPR in 2023, and 23 or 24. He gave a talk. He said, he has learned all these things from computer vision. So this is, pretty impressive that if you can generate images, video, you can generate proteins, and proteins can give you different vaccines and can save lives and so on. So which is that's a good thing about science, that once you understand the basics at intuitive level, very simple, right? Then you can apply those to different things. And they are actually also discovering new materials, using this kind of thing. So there's a lot of application. So, but right now, the hottest thing on the Twitter is that these videos, you can generate these amazing videos, which looks very real. And that's why the Hollywood is getting concerned, right? Because if you can, make the movies, using, because if you can have a prompt to generate a video, and if you take the screenplay script sometime in 5 years or 10 years, just dump in that to generate a video which looks very real. So which is, really big breakthrough. So one can build upon, these kind of things that, what are the new application of this basic method. Right now, if you look at these videos, these are very small, short videos. These 16 frames, 30 frames, and so on. Few seconds. So that's a limitation. So if you want to generate a 5-minute video, it's not possible, right? Because you need a lot of computing power. And so we talk about UNet. It started with UNet, but now the best way to do this diffusion model is transformer. So there's a special transformer called DIT, diffusion transformer, right? So the guy, I think he had a paper in ICCV, then he went to OpenAI, and he came up with his transformer model DIT is for images, but then he went extended to video, and they can generate very impressive videos there. So the question is that if now in principle, you can take, say, video clips, say 16 frames, right? Here, you take one image, say 100 by 100, 10,000. Now, 16 times 10,000, it's more, but this is only, 16 frames. So if you do that, then, this attention, so each frame, say, 200 tokens. So 200 tokens multiplied by 16, a lot of attention. But this is only 16 frames, which is one fourth of the, 1/2 of the second. So if you want to generate a 5-minute video, there are ways, how can you do the attention? And that's where the things come in, that what are the innovative ways to reduce the, attention. You can maybe do sliding windows. We talk about swing transformer, that shifted window. So look at local neighborhood and so on. There are lots of innovative ideas you can bring in to this, but the main thing is that you have to know the basics, and then you can, it's open, you can do, come up with a new idea, and that's what research is about. And you guys will be working on the research projects. Okay, any comments?